All right, let's do the chapter 4, which is an introduction to differential equations. So some of you might be moving on to take an entire course on differential equations or multiple courses. This is the topic that's still widely being studied today, but we're going to do the introduction today. So some basics of differential equations. First off, the definition. A differential equation is an equation that has a differential in it. That's kind of the biggest part of it. So it's an equation that involves an unknown function. Typically, we call an unknown function y or f of x or some combination of those. And then one or more of its derivatives. So maybe y prime or f prime or dy dx. Various notations represent the same thing. So here is an example. This is an equation that involves an unknown function y. Y does not equal cosine of x in that case. Y is something else. I don't know what it is, but I do know that y prime, so the derivative of whatever y is, maybe it's sine, I have no idea, plus 4 times y is equal to cosine. Okay, that's a differential equation. And then the solution or the general solution that we're looking for in a differential equation is that unknown function. So we're not looking for like an x equals 12. We're looking for a function. Maybe it's f of x equals 3/4 sine of x plus cosine of x, whatever that function might be that would satisfy this equal sign. That is going to be the solution to the differential equation. So a couple of things to note: y prime plus 4y equals cosine of x is a first order differential equation because it has only the first derivative. Same thing for this dy dx equals cosine of y plus t squared is also a first order differential equation, and that probably should have been an x squared. That was maybe a typo there, because the highest derivative it has is the first derivative. Then that last example has a second derivative, so the highest derivative is the second derivative, so it's called a second order differential equation. So if it had a y triple prime, then that would have been a third order, and so on. The order is the order of the highest derivative involved in the equation, and the solution, or the general solution to the differential equation, is a function that satisfies that differential equation. So let's just practice. So we're going to check to see if something is true or not. So to verify that y equals e to the negative 3x plus 2x plus 3 is a solution to this differential equation, the only way to verify something is true is to plug it in and see if both sides of the equal sign are equal. That's literally what we do. So I'm going to plug it in, and I'm going to write out my differential equation so it's all on one line. I have y prime plus 3y equals 6x plus 11, and then I have that this is the solution, so I'm going to plug that in everywhere I see a y. Okay, so it's going to become an e to the negative 3x plus 2x plus 3 prime plus 3 times e to the negative 3x plus 2x plus 3 equals 6x plus 11. And then prime means take the derivative, so negative 3e to the negative 3x plus 2. And then I'm going to distribute. All I'm doing here is simplifying along the way. The left-hand side, in this particular example, and everyone's going to be different, but in this example, the left-hand side kind of requires a lot of simplification. The right-hand side, there was not really any like terms to combine. And then on the left, this guy and this guy cancel, and I ended up with 6x plus 11 equals 6x plus 11. That is a true equal sign. So that is the verification. The verification is not that last line. The verification is all 4 lines. The work is what matters here the most. The work matters. There isn't like a final answer. Again, that's not how this works. We're telling a story. Okay. So that's the verification that this function is a solution to that differential equation. Okay, so let's check again. So here's my question is worded a little bit differently. I'm not saying verify. I'm asking a yes or no question. Is this a solution to the differential equation? So how do I know if something is a solution to an equation? Well, you plug it in and you see if both sides of the equal sign are true. So I have a y equals c times e to the x squared. I'm going to plug that in everywhere I see a y. So it's a dy dx where I replace my y with c e to the negative x squared equals 2xy, where I've replaced my y with c e to the x squared. And now on the left, that d dx is the operator. Take the derivative with respect to x. C is a constant multiple. It will stay. the derivative of e to the x squared is e to the x squared times 2x. That was using chain rule. And then I'll just simplify it. Maybe you don't really need to simplify it. You can if you'd like. Can you see without me having to reorder anything that those are in fact the same? So they are the same. So therefore, the answer to this question is yes. If they were not the same, then the answer to that question would be no. Let's practice again. Same question. It's a yes or no question. Is this a solution to that? So is y equal 3 sine of 4x plus 5 a solution to the differential equation y double prime equals negative 16 times the quantity y minus 4? Now I'm going to plug it in. That's how you check. That's how you check. You have to plug it in. Now this particular problem is a second order differential equation, so it's going to require two derivatives. So what I'm going to do is I'm going to take those derivatives first off to the side, like some scratch work. I'm just not sure I can do two derivatives in my head. That's something I recommend that you guys do as well. So I'm going to just start off with the y equals that was given to me, and I'm just going to take two derivatives over here to the side. So the first derivative is 3 cosine 4x times 4. I don't know if I did that correct. That looks like I did. Yep. Plus 0. And so then that means y double prime. Let me rewrite that then. 3 times 4 is 12. So y double prime would be 48 times negative sine of 4x. I don't need to keep writing that plus 0. Okay, that was me just doing a couple of derivatives off to the side because I wasn't sure I could do those all in my head. Maybe you can, maybe you can't. Okay, and then I'm going to go over here and plug it in. So I'm going to rewrite my differential equation. I'm rewriting what my differential equation was, and I'm now going to take what I think sorry, I didn't circle the right thing. Take what I think the solution is and plug it in. So my y double prime is, I don't need to reinvent the wheel, it's negative 48 times sine of 4x. I did that already on the left. That's why I did that scratch work. Equals negative 16 times 3 sine of 4x plus 5 minus 4. Excuse me, I'm going to highlight some stuff so you can see it. That y double prime came from the work I did earlier. And then this y, I replaced it with what y is. Okay, maybe that's too much highlighted on the screen, but hopefully you can see where that's coming from. And then I just have to simplify. In this case, it looks like the right-hand side has more to simplify. You never know. You oftentimes have to simplify both sides of the equal sign. So just don't forget to keep both sides of the equal sign. It looks like I have a negative 48. I'm distributing the sign, or sorry, I'm distributing the negative 16 minus 16. Yeah, I distributed the negative 16. Feel free to use your calculator, whatever it is that you need. Just make sure it's simplified. And then I could bring add 48 sine of 4x to both sides of that equal sign. And I got 0 equals negative 16, which is not true. So the answer to that question is no. It was not a solution. It was just a yes or no question. Is this a solution to that differential equation? No, it didn't work. It did not give me a true equal sign. Although it was pretty close. You have to admit, it felt really close. Let's go back a little bit. So the answer to that is no. Everything I have there, that's it. So maybe pause what you're writing and just watch with me for a second. It was so close. If this negative 16 were not there, then this would have been a true equal sign. How did that negative 16 get there? Well, that came from 5 minus 4 is 1, and 1 distributed across to that negative 16. So if there was no 5 minus 4, if that was like a 5 minus 5 or a 4 minus 4, we would have been good. So if this were a 4, we would have been good. So let's just make it a 4. Yeah, so now I have a general solution. I have a general idea, at least, of how to find a solution. So if that is, and you might want to notice that, make a note of this, y equals 3 sine of 4x plus 4 is a solution. All right, so you could have done that by redoing the whole work with the plus 4 instead. The only thing that would have changed is that would have been a 4, which means that would have been a 0, and I would have gotten a 0 equals 0, which is true. Okay, let's do some more. Now you're going to ask you to solve the initial value problems. An initial value problem is a differential equation with a condition. So it has a condition in here. So here is a differential equation. I know it's a differential equation because it has a derivative and an equal sign, and that's all it takes. I like to rewrite it with Leibniz notation. That's the habit that I'm in. It's a good habit when these get harder. So when these get harder, you need Leibniz notation. You can get away with Newton notation when they're nice and easy though, so it's up to you, but I recommend you start getting into the habit of Leibniz notation because when they get more difficult, it's going to be a requirement. But either way, here it says the derivative is equal to 3t squared minus 4t plus 10. Remember a differential equation to find the solution, you're looking for the y equals. So how do I undo a derivative? You just integrate. Yeah, literally, you just integrate both sides. Now, technically, I'm integrating both sides with respect to t. So technically, that dt sort of cancels, if you will. And then the antiderivative of 1 dy is just y. And then you do the antiderivative on the other side, which is t cubed minus 2t squared over, I'm sorry, that's not the antiderivative. Let me fix that. 4t squared over 2 plus 10t plus a constant. Don't forget there was a constant there. And so now I have a y is equal to t cubed minus 2t squared plus 10t plus a constant. And now I use the initial value. I recommend that you write that initial value as an ordered pair to help you get used to the x comma y. So I know which one to plug in for my y and which one to plug in for my x. Here y is 20 and x was 0. So 20 equals 0 cubed minus 2 times 0 squared plus 10 times 0 plus c. These numbers happen to be easy. I promise it will not always be this way. So then that means that my final answer is t cubed minus 2t squared plus 10t plus 20. Ta-da! Again, same question. This really is kind of repetitive, I know, but that's the best way to get the extra practice. Another initial value problem. First things first is to get rid of the derivative. So I'm going to just write that integral on both sides of that equal sign. You're integrating with respect to t. On the left-hand side, you're going to have a y. On the right-hand side, I need to figure out how to do the antiderivative of 8t squared times e to the 4t. I don't know the antiderivative off the top of my head. I could try a u sub, it wouldn't work. It's a integration by parts. And it's actually a tabular method. So now's a good time to practice the tabular method. I can think about Liate and go through the tabular method. I would have had to use 8t squared as my u, and its derivative eventually goes down to 0. And so I get to do this shortcut trick tabular method, 1/4 e to the 4t. I'm filling in antiderivatives on the other side. Diagonal multiplication, plus minus plus minus. So then I have 2t squared e to the 4t minus 1t e to the 4t minus 1/4 e to the 4t. I simplified along the way. Plus t plus a constant. Pay close attention to that plus 1 out there. Don't forget to do that antiderivative of that guy as well. Okay, and then I'm going to do my initial value. With my initial value, I always recommend you write it as an x comma y or t comma y. So you know this is t, this is y, so I know that 5 is the y value. If I plugged in 0, this would have been a 2 times 0 minus a 0 minus a 1/4 times e to the 0, but e to the 0 is 1 plus 0 plus c. So I actually ended up with c is equal to... sorry about that. Yeah, I did miss a negative. Let me fix that. That was a positive 1/4. Positive 1/4. Now my negatives are correct. So I got c is equal to 5 minus 1/4. So c is equal to 19/4. So then you rewrite the final answer as y equals, I'm going from the final answer, 2t squared e to the 4t minus t e to the 4t plus 1/4 e to the 4t plus t plus 19/4 is the particular solution to that differential equation with that specific condition or initial value. Ta-da! All right, that's the basics of differential equations. You have a differential equation, and the question is to try to find the unknown. And the reason why that might be helpful is oftentimes we know how things change. but we don't necessarily know what they currently are right now. So like we might know the general average temperature change that's happening in this city around this time of year. And then we're trying to get a pattern to see what's happening. Maybe we can solve a differential equation to get a model for what might happen in the future. So this is all about maybe you already know how something is changing, and that's a derivative, and you're looking for what it might be. It's the original function. So the function would be the unknown. The differential equation is what we're trying to solve. Okay. All right, so I'm going to continue on with 4.3. We're doing 4.1 and 4.3 sort of combined here. 4.2 is graphing these. For those of you who want to look it up, you can graph those. Certainly welcome to. It's not particularly exciting for right now, but you can. 4.3 is a continuation of the exact same thing. We're still trying to find a solution. Okay, so it's literally exactly the same as 4.1, only it has a new name. It's called separable. Separable differential equations are equations where it's possible to get x's on one side and y's on the other. And that's what we're going to focus on in 4.3. So there are things that are not separable really quick. And I think it's worth our time to at least see something that's not separable, like y prime plus y equals sine of x. You would rewrite that as dy dx plus y equals sine of x. Right now I have x's. This is hard to see, but I do have x's on both sides of that equal sign. Oh, it's hard to see because I've got it covered. Sorry, now it's a little bit better. I do have x's on both sides of that equal sign. And you could try with all your might to get all x's on one side and it wouldn't work. If I tried to multiply everything by dx, I would then have a dx right here, and I would still have x's on both sides of the equal sign. So this is not separable. These are ones that you're going to solve when you take your differential equations course. There is a ton of material for that course. It seems so simple, but I'm telling you, it's actually kind of hard to solve, even though it seems so simple. So we're going to focus today in Calc 2 only on ones that can be separated. So x is on one side, y is on the other. Or t is on one side, x is on the other. Whatever the letters are, just separate the variables. That's what a separable differential equation is going to be about. And so in this case, I still highly recommend that you write things in Leibniz notation. I don't think it's required, but I think it's more visual. And so it's helpful to keep track of things. It's certainly not required, but it's just going to be a matter of keeping track of some stuff. So I'm going to separate my variables. It doesn't look like it's separable here, but it is. I'll show you. I'm going to divide everything, both sides of that equal sign, by negative 2y minus 4. I'm doing both sides of that equal sign. And then on the left-hand side, that's going to become dy dx over negative 2y minus 4 equals 1. And believe it or not, this is separable because I could integrate both sides of that equal sign with respect to x, and then your dx cancels. Doesn't like really cancel. It's not quite the right vocabulary term, but it always works. So it's very convenient to do this because this will always work. And so now you have y's on one side and x's on the other. So you can continue on until you get a y equals. The idea is to get a y equals. So that's what we're going to do. On the left-hand side, I'm just going to rewrite what I have. I had a dy over negative 2y minus 4. And then I had the integral of 1 dx. So on the right-hand side, it's x plus a constant. On the left-hand side, it's linear on the bottom. So I do get an ln, but don't forget to divide by the constant multiple, just like we've been doing. And I'm going to call that constant C1 because we're not done with this problem. We have to do all the algebra now, and this is what's going to make 4.3 a little bit harder. What I mean by doing all the algebra is you have to keep going until you get y equals something. So I'm going to multiply both sides by negative 2, and I'm going to write that down. And I know you don't always write that down, and you certainly don't have to always write it down, but I'm going to show you why it's helpful, because you are going to distribute. So this is going to become an ln of negative 2y minus 4 equals a negative 2x minus 2 times c1, but c1 was just a constant. So 2 times a constant is just a different constant. So I called it c2. It's just different. You can call it q if you like. It has to be different though. You can't call it c again. You cannot call it c1. It has to be something different. You cannot still call it C the whole time. It won't work, I promise you. So be very careful with that notation. And now I'm going to try to get y by itself. So I'm going to use properties of logs, which is exponentiate both sides of that equal sign. I'm going to get e to the negative 2x plus c2. that whole thing is in the exponent. The ln and e to the something canceled on the left-hand side. So e to the negative 2x times e to the c2, because when you have a plus in the exponent, this is the properties of exponent, e is a number. E is a number. It really is, and it always has been. E is a number. So e to the power of a constant is just some number. So I'm going to make that e to the 2x times a different number. It is different, so you have to label it as different. Okay, and then I'm going to keep going. So then I have a negative 2y equals c3 e to the negative 2x plus 4. And then I'm going to finally divide everything by negative 2. And then we're good. But I'm going to show the work for that. Divide everything by negative 2. And then that will become a y equals c3 is a number, negative 2 is a number. So now it's a different number. It has to be labeled differently. It does. It has to be, because it's different. You can't say two things are equal unless they're equal. They're not equal. So you don't get to call them the same because they are not the same. So it's as simple as that. Ta-da! Now you got your y equals. So this is the general solution to that differential equation. Okay, let's practice again. This is a common one. This is a classic Calc 2 question. It's going to show up again, I promise. So I'm going to rewrite this. You might rewrite this right away as dy is 2y plus 6 times dx. That's a common thing people do. I tend to not do it this way because there's some technicalities around those differentials that make this not quite true, but it's convenient to treat it as if it's true. It's the same thing as just doing the integral on both sides of the equal sign with respect to x. So it works out just fine. And then I would get a dy over 2y plus 6 equals dx. And I'm integrating both sides of that equal sign just like I've been doing. It's linear on the bottom. So ln 2y plus 6. Don't forget to divide by the constant multiple. And don't forget to call the first constant of the problem c1, because that will have to be different later on. And then I multiply both sides by 2. And I'm going to get 2x plus a different constant because I multiplied it by 2. Then I'm going to exponentiate, which is just e to the power of 2x plus c2. It's just e to the power of, and then that becomes 2y plus 6 e to the power of 2x times e to the c2. When you have a plus in the exponent, it becomes times with the same base. And then e to the c2 is some other constants. So then you have a 2y equals some constant times e to the 2x minus 6. And then I ran out of space, so I'll just divide everything by 2. And I'm going to get c4 e to the 2x minus 3. Ta-da! Cool. These are that's all there is for a separable differential equation. The hardest part, I think, is the algebra, but also remember you have to know these antiderivatives. So like you might have to use an integration by parts at some point, or a trig sub, or partial fractions, all of that. So all of the integration strategies are still valid. So just make sure you're careful with practicing along the way. Again, so same kind of idea. I'm going to go in a du. I'm going to write it out. Du divided by 3u minus 1 equals dx. I'm integrating both sides of that equal sign. 1/3 ln of 3u minus 1 equals x plus c1. Don't forget to call it c1 because it's going to change. Multiply both sides by 3. Now it's c2 because it changed. And then exponentiate both sides. And you know that that e to the power of c2 can come down as a c3. And then I'm going to go add 1 to both sides and divide by 3. But then in this case, I have an initial value. So one more time, I recommend you write it as an x comma y. In this case, it's an x comma u, because this was a du dx, so you can think of u as your y. And then I know where to replace things. Then I have a 6 is equal to c4e to the 3 times 1 plus 1/3. Of course, I ran out of space. So 6 equals c4e cubed plus 1/3. Subtract 1/3 from both sides. And when you subtract 1/3 from both sides, don't forget to use the fraction button to make sure you leave things correct as equals as an exact value, c4e cubed. So c4 is equal to 17 over 3e cubed. And that's not the final answer. Your final answer would be the solution to the differential equation. So u is equal to C4 times e to the 3x plus 1/3. Ta-da! All right, let's do a little bit more, just a couple more. We're doing really good. Determine if they even are separable, and then if it's separable, you can solve. So that's kind of the big picture for this one. Sometimes they're not separable, and if it's not a separable differential equation, you will not be expected to solve it in Calc 2. We're only doing separable for right now. Okay. Here's an example of one that's not separable. You could try. You could really try. dy equals ty plus 2 dt. I can't divide by that whole thing because that would give me t on both sides. I can't divide by just y, because if I divided by just y, then this would end up with a 2 over y, and then it would have y's on both sides. It's not going to work. So this one quite simply is just not separable. This next one is, I ended up with dy times y equals 3t squared dt. You can think of that as cross multiplying. There was a technicality about when I took the integral of both sides of that equal sign, but it's the same kind of idea. So I ended up with a y squared over 2 equals t cubed plus some constant. So y squared equals 2t cubed plus 2 times c1, which is 2. So y is equal to, don't forget, when you take the square root of both sides of the equal sign, you end up with a plus or minus. Ta-da. Again, so same kind of idea. This is why I think Leibniz notation might help you visualize it. dy dx is x squared times y will give me dy over y is x squared dx, and that's what I'm integrating both sides of. And so then I would end up with ln of y. So this is separable because I was able to separate my variables. ln of y is x cubed over 3. So y is c2e to the x cubed over 3. Ta-da! Cool. A lot of it's kind of extra practice of the same thing. I'm going to skip part D. Now's a good time for you to pause and try to work that on your own. It's good practice for you. Let me move on to part E. So same kind of question. I would rewrite that as dy over 2y plus 1 equals, when I bring the dx to the other side, it's on top, and then I would have to have divided by the x squared plus 7, so it's on bottom. And then when I integrate both sides, a little bit trickier. This is going to be linear on the bottom, so it's still ln, but don't forget to divide by that constant multiple. And then over here, you can try to do a trig sub if you'd like. Here I would do a trig sub for the right-hand side. I would let x equal the square root of 7 times tangent of theta. And then do the trig sub. You might need to go back and look at your trig sub notes to solve that. Pause the video and solve that one using the trig sub. I ended up with 1 over the square root of 7 times arc tangent of x over the square root of 7 plus a constant. Multiply both sides by 2. And I would end up with 2 over the square root of 7 arc tangent of x over the square root of 7 plus a different constant because I multiplied by 2. And then finally exponentiate both sides. 2y plus 1 is c3e to the power of, the c3 came from the e to the power of c2 is a constant. And then e to the power of the rest of it, which is 2 over the square root of 7 arctangent of x over the square root of 7. And then last but not least, subtract 1 and divide by 2. So y is equal to c4e to the 2 over the square root of 7 arctangent x over the square root of 7 minus 1/2. Ta-da! Okay, and then I want you to take a look at part E and part F. Look how real similar they look. They look very, very similar. Strange. We can do it though. There is a subtle difference. This one was a dy dx is what made that a differential equation. That's where the derivative is. And this one is a dx over dy. It's just a good reminder to know that which one means what. So dy dx means that y was a function of x. Now this means x is a function of y. So when I had a dy dx, I was looking for a y equals. When I have a dx dy, I'm looking for an x equals. So it just changes what variable you're solving for. Yeah, that's all. So in this case, this is going to become an x squared plus 7 times dx equals a 2y plus 1 dy. I didn't need to divide anymore. It already is separated. So then when I integrate both sides, I'm going to get 1/3 x cubed plus 7x equals y squared plus y plus a constant. I would try to get x by itself. But this is an example where it's actually impossible to get x by itself. Sometimes that happens. So this is called an implicit solution. It just means it wasn't algebraically feasible for me to get x by itself. So it's called implicit when I don't have the variable all by itself. Ta-da! All right, that's all there is for differential equations. That's the basics of differential equations, what they are, how to verify if it's a solution, and what separable differential equation is. That's all we're doing for this one. Thank you.